So one of the critical documents that we talked about was the borings, and another was the geotechnical report. So part of our contract for MnDOT was to develop a FADR, and so we're going to talk a little bit about that in this lesson. This is a fairly brief lesson. Also kind of give you some background on why we chose drilled shafts for some of the foundations at the Red Wing project. And as John said, we're looking for an effective way to transfer structure load down into competent bedrock, get the load of the bridge into the earth. So that's why we ended up with drilled shafts on this, and we'll get into why. First, a FADR, the acronym Foundation Design and Analysis Report. It's a typical document. The name FADR is pretty unique to Minnesota, but it just means the geotechnical report. So we prepared the FADR, and it was submitted for review by Paul and his group, and Rich Lamb and his group as well. In that document, you will find a discussion about geology. I'm not sure what level of detail as an inspector would need to understand the geology, but some general knowledge of the setting is probably beneficial. And there's a write-up in there as well, so if you're interested, read through it. It also gives a description of the subsurface investigation for the Red Wing project. The borings were conducted by MnDOT with their in-house drill crews. I forget the number of borings, but there are a few borings at each Pier 1 and Pier 2, which are the locations of the drilled shafts. So part of the subsurface investigation is not only the field sampling and testing, that's the borings, or CPT, but also the lab testing that went along with samples that were recovered from that investigation. So in addition to the geology, which is more general overview of the setting, we also describe the subsurface conditions. So this is a beneficial document to review to understand the obstructions we talked about. What do we expect we're going to encounter? Do we expect obstructions? What kind of geomaterials do we expect to come out of the ground? So there's a description of the subsurface conditions that are anticipated. Not only do they affect construction, but they also have a great influence on the design of the drilled shafts. Foundation analysis, that's the calculations that we do, the numbers that we crunch. As John said, we're relying on both side resistance and base resistance. So those are primary players in the calculations that we perform. Those calculations are described in the report. If you want them in detail, you can have them, but they're probably not ultra critical for the inspector. And then, of course, the recommendations. Following the number crunching we do, the analysis we do, we develop recommendations for Paul to put on his drawings. How big do the shafts need to be, or what kind of resistance can we get out of the drilled shafts, both axially and laterally? And then also some construction requirements. So we're counting on base resistance. We got to make sure we got a clean base. There's discussion of that in the foundation recommendations. Ideally, the foundation or the construction recommendations in a FADR get transferred into the special provisions or construction specifications. In this case, I know that they have. The subsurface conditions we're dealing with at Red Wing, this is a Rich Lamb special, this drawing. He's renowned for putting together his colored pencil drawings, and they're always very beneficial. You can see Pier 1 is the one on the Minnesota side. So it's what I would call the high bank side. So there will be drilled shafts that will extend through this sand layer and down into this sandstone bedrock. As you head across the river and into the Wisconsin side, you can see the level of bedrock declines rather dramatically. The soil, the overburdened soil above the bedrock, very typical of a Minnesota or Mississippi River deposit in Minnesota. So we've got alluvial deposits of various layers of sand, organic silty clay. Really, the organic silty clay is very soft, very compressible material, a problem soil that you guys deal with in Minnesota all the time and in Wisconsin as well. Some gravel zones, okay, well that's interesting. We got to be thinking gravel that could maybe stop a casing as I'm trying to advance a casing. I've got drilling fluid that I want to keep a positive head inside the casing. Well, if I got drilling fluid, could it leave through the gravel? Obviously, gravel is very porous. So we don't want to lose all of our fluid head, and then sand, and then of course the sandstone. Conditions driving the Pier 1 and 2 foundation design, so that's where we have drilled shafts. As David mentioned earlier, we've got large lateral vessel collision. Okay, so we're in the Mississippi River. We're subject to fully loaded barges moving either upstream or downstream under power. And oftentimes, Paul, correct me if I'm wrong, but a lot of bridges that are designed these days, the bridge pier is going to win the battle with the barge anymore. I would say maybe 30 years ago and before, a lot of times the barge would win that fight. But now the bridges are being designed, basically the force that we're imparting is the crushing strength of that barge hull. So the force that's getting into the bridge is what it takes to crush the barge. So by definition, the bridge is going to win the battle if we get a hit. But it's an enormous load. Okay, that's a really high lateral load we got to design for. And so that drives the foundation diameter size, particularly at Pier 1, if I recall. We're in a river, okay? We said it's alluvial soil deposits. The river put the soil there. The river can take the soil away again sometimes. So when we have deep scour and a long unsupported length, imagine you drive a 12-inch diameter pipe pile, or a bunch of them even. No problem. It works all the time. We've got a lot of bridges sitting on them. They work great. But when a lot of that soil gets scoured away, now we've got these little tiny noodles holding up our bridge, okay? So they work great when they're confined, but when the scour takes the confinement away, the soil away, sometimes we can have a problem with this unsupported length. Turns into a flagpole. Subsurface conditions. We want to transfer that load from the superstructure down into the rock, into a competent rock. Not only to the top of it, but since we have scour, we need to get that load into the rock. If we set it on top of rock, that'd be fine for a while until we lose the scour. Then we've got nothing laterally to hold our bridge in place. So the subsurface conditions, where the bedrock is, we want to get the shafts into rock so that we can have a structural connection between the bridge and the rock. It's a big bridge. It's a Mississippi crossing. It's got a big main span, so there's quite a bit of demand on it. Not only the weight of the structure, but other loads, the traffic loads, and other things that get applied as well. Footing size. We're going to have one pier in the river, and we're going to have one pier right on the bank. There's some railroads over on that side too. With drilled shafts, they're very efficient to get load to rock. So we can put really a high axial demand on them and lateral demand on them as well. By using a bigger foundation, a bigger shaft, or bigger piles even sometimes too, oftentimes we can reduce the footing size. If you got a lot of small members and say you've got a 3 diameter center to center spacing between piles in a group, if you got small piles and you got to space them out that way, it turns into be a bigger pile group. That's an important point in the river where we have a coffer cell. Obviously we all know that coffer cell is one of the higher risk items in construction. If we can reduce the size of a coffer cell, we're usually doing ourselves a lot of good. In addition, the bigger that footing size is, the bigger obstruction is to navigation, the bigger chance for additional scour because of a big footing. So there's a lot of benefit in the river about reducing footing size. That lends itself really well to drilled shafts. So what we're going to have at Red Wing, Pier 1, we'll have drilled shafts, permanently cased down to sandstone, and then our rock socket. There's a 1x2 group there. We'll get into that more in the next lesson. At Pier 2, which is the one in the river, which could be constructed within the confines of a coffer cell, you'll note that the footing is mostly buried. There's a little bit of sticking up above the mud line, but not much. The top of that's what, 15 feet or 16 feet beneath the water line? Yep. Something like that. So it's going to be a pretty deep coffer cell by the time you get to the bottom of the footing, and then a little bit deeper for the seal slab too. But again, we're going to have drilled shafts, a 2x2 group of drilled shafts, permanently cased down to rock, and a rock socket. All these other piers, you may be asking yourself, well, these are on driven piles, HB 14 by 117. So beefy pile sections, but they're driven down to refusal on rock. So you can see we got driven piles and we got drilled shafts. So why the difference? Well, if we remove this material due to scour, and I will offer, we're not the people estimating the scour depth, and the more we work with bridges like this, the more the scour holes seem to be getting deeper and deeper and deeper. But so, these driven piles, which are actually relatively noodly members compared to a 9 or 10 foot diameter drilled shaft, they work a lot better when they're not exposed to this scour. So when the scour happens, that's an entire length of unsupported shaft. So that's just a column. That's just a reinforced concrete column holding up any load. It could be it's like a building. So that could be on the order of 40 or 50 feet deep. So you can imagine how much flexural strength you need for a column that's 40 or 50 feet tall. And that happens after the bridge is already built, when the scour comes and takes all that soil away. So why do we end up with drill shafts? Okay, we said we got a high lateral strength and stiffness. Lateral strength is a function of the diameter, to the fourth power, in fact. And so by having larger diameter, you got a lot stronger lateral response, flexural strength. And so, you know, a 10-foot diameter, it's can offer a lot more strength and stiffness to resist vessel collision after scour than a pile can. We can get that load not only to the top of rock with drilled shafts, we can get them into the rock. So when the soil goes away, we don't compromise the integrity of the structure. All our load is still getting into a material that's not scourable in our lifetime. Fewer number of piles, so that reduces the footing size. A lot of associated benefits with that. Smaller obstruction navigation, less scour potential when the footing size is decreased, less risk. So if you can minimize the size of foundations, often it's in your benefit. All right, groundwater. There were a lot of folks in here that said they had experience with the 35W replacement in the St. Anthony Falls. A great example of artesian pressure, or groundwater in the shaft that is above the static river level. And the reason being, if it's a Red Wing anyway, say you've got a water surface, something like so, but water is entering the aquifer somewhere at a higher elevation, and say that entire aquifer is charged with groundwater. Well, when you drill a hole, you could have a well. That water is going to want to flow out. It's going to follow the path of least resistance, and if that path is up and out of the hole, then you have an artesian water condition, which can play havoc on hole stability, excavation hole stability, cleanliness, because as the water's flowing into your shaft, it would be bringing junk. And also when you have fluid concrete, if water's flowing into that fluid concrete, imagine what's going to happen to the concrete. It's like when you pour your sidewalk and then you go out and spray it with a garden hose, you're going to be left with nothing but a pile of aggregate. We can get the same thing if water's flowing into our fluid concrete. We don't want that. At all times, we want our water or our drilling fluid pushing back out. If anything, we want it flowing out, not letting stuff flow in. The only way we get that is by keeping a positive head. At Red Wing, we don't have any indication that there is artesian conditions, but it's St. Croix and very similar foundation materials, sandstone, this very similar sandstone formation. We did notice artesian pressure on the order of a few inches where you can see water flowing out of the top of the casing. We want to avoid that. Contractors got to be prepared to handle that. Easiest way to do it, leave the casing tall so that you can build up a head that's greater than the artesian head. It's a solvable problem, but they have to be aware of it. Okay, all right. So Pier 1, the conditions that we have. Top of the shaft, which is going to be the bottom of the plinth, elevation around 668. So we've got about 35 feet of primarily sand, pretty dense sand, okay? Top of bedrock, we show those little wiggly lines, estimated elevation 632. So really in the scheme of things, not a very long shaft, okay? Permanent casing down on the top of rock, of course. Top of rock here, there's a bridge right next door to it, existing bridge with driven piles, and we have the driven pile records. So we have a pretty good feel for where the top of rock is based on where those adjacent piles took up. So we feel pretty good about the elevation 632, but the rock's sloping, we show that on the picture. So there could be some changes. We're estimating tip of casing at 630, 2 feet of embedment. That's a guess. The casing, if the casing stops and can't go any further, the casing stops. It becomes a problem possibly for the contractor. It becomes a constructability issue. Not necessarily a problem, but a constructability issue. If it can't be sealed into rock, they just got to make sure that they keep a positive head. It means they may have to use more drilling fluid as that drilling fluid's pushing out. It's a solvable problem, but it's tough to guess where the casing is going to stop. And then the tip of shaft, it's a 14-foot socket. So we tip down in this glauconite sandstone. Recovery and RQD don't look the best. They're low numbers, but that's pretty typical of this softer sandstone. We saw the same thing at St. Croix, yet we still measured fantastic axial resistance in a load test. Pier 2, this gives you an idea. Of course, we're in the water here now. The silty clay that I said was a bad acting material that's common around here. You can see weight of hammer. That's the SPT blow counts. Basically, when you see weight of hammer or low numbers, that means very soft, compressible material. So we don't get much axial resistance out of that, but alternatively, it should make for easy drilling. Then, we get through 40 feet of very soft material, some sand and gravel. I would expect, what we've seen in the past, there might be a boulder or two in there. So there could be some headache-sized particles in this sand and gravel above bedrock. Nothing that we won't be able to handle, but we could expect to see some boulders in there. And then again, we have tip of casing that's estimated, and we have a rock socket in the sandstone. So the takeaways from this: the FADR, our geotechnical report, it's your reference that you can have an understanding of the subsurface conditions before you get out there. You can see what our assumptions were, how we developed the design. Where's the sand, where's the soft clay, where's the rock, how good's the rock. Our interpretation is dictated or expressed in the FADR. Boring logs are in there as well, but they're also on your project drawings. Gave you a very brief general understanding of the subsurface conditions. Sand above bedrock at Pier 1, sand and soft clay above bedrock at Pier 2, and Pier 2 the bedrock's quite a bit deeper. Drilled shafts were selected because it's an effective way to account for the scour, to handle the large lateral effects from vessel collision, and to get the loads down into the rock.